is Yoon Chung, and I will talk about our paper, TailedCore. Few-shot sampling for unsupervised long-tail noisy anomaly detection. We discuss about a novel unsupervised anomaly detection task, namely, noisy long-tailed unsupervised anomaly detection. Specifically, normal data is both contaminated with defective regions, and the product class distribution is tailed, but the tailed classes are unknown. Previous methods addressed either only noisy dataset or long-tailed dataset. However, the setup where both happens together is realistic. Hence, our suggested scenario is highly practical. Previous methods to solve either noisy dataset or long-tailed dataset suffer from tail versus noise trade-off, where a noise discriminative model shows low performance on tail class samples, while algorithms, such as greedy sampling, favor tail classes due to its nature also favors noisy features. To mitigate the issue, the tail class and noise samples should be handled independently. To this end, we propose TailedCore, which separates the tail classes exclusively with tail sampler, a novel class size predictor that estimates the class cardinality of samples. Specifically, tail sampler uses the global average pooled features of samples which are less affected by anomalies, as most of the anomalies are local. After tail classes are sampled, we utilize a noise discriminative model for denoising and merge the features from each samples. To explain more specifically, we first estimate the class size of each samples. First, we search the set of neighbor embeddings HI of embedding EI as shown in the equation using cosine similarity for every embedding EI, where MI is the maximum angle between EI and every other embedding Z. We define the adaptive angle alpha as the equation which contains the PTH percentile of the half maximum angle region. Then, we estimate the class size of embeddings based on the neighborhoods of neighborhoods, where N alpha EI is defined as the equation, denoting the neighborhood of EI, which is the set of all train embeddings E within angle alpha of EI. Then, class size is estimated by the mode of the equation of kappa, where alpha E is the adaptive angle with respect to embedding E belonging to the neighborhood N alpha IEI of embedding EI. With the acquired kappas, we estimate the size of each class's ETA inductively by the equation below, and finally, determine the maximum size of tail classes with elbow technique. We conduct experiments on 3 different types of long-tail setups, which are Pareto, step k equal 4, and step k equal 1, where k denotes the number of sample for the class. For the step setups, 60% of the classes are long-tailed, and the head classes are all contaminated for all setups. We present our results comparing with different anomaly detection methods, including few-shot anomaly detection methods such as when clip and anomaly clip, noise discriminative methods such as soft patch. Our method exceeds other baselines on 2 datasets, which are MVTech AD and Visa. Our method outperforms few-shot methods with noisy samples, as you can see on the performance on head classes, denoted as CH, which are contaminated. In addition, our method performs better on noise discriminative models, especially on tail classes denoted as CT. We conduct ablation on the noise ratio on 3 different methods, and the results are shown as below. As shown in the graph, the performance of patchcore deteriorates as the ratio of noise increases, while TailedCore and soft patch is relatively less sensitive to the noise ratio for every experiments. Another remarkable fact is TailedCore is comparable to patchcore when the dataset is noise-free, while soft patch doesn't work well in this setup. Additionally, we try to discover the correlation between several factors by the classification accuracy of tail classes and noisy samples, shown in the x-axis, versus metrics, shown in the y-axis, relevant to class size prediction and few-shot sampling with step k equals 4. Correlation is strong for A. Missampling ratio, B. Ratio of missing few-shot samples, E. Class size prediction error, and F. OROC for few-shot prediction. Better embeddings improve tail sampler, which in turn improves G. Anomaly classification, image level OROC, and H. Anomaly segmentation, pixel level OROC performance. Finally, the figure below shows the segmentation quality of some of the samples from different baseline methods. That's over for the presentation, and thank you very much for listening.